We can divide matter up into two basic types. It's either a pure substance made up of just one thing, or it's a mixture of substances. Pure substances can be further subdivided into elemental, things made up of one type of atom, such as gold, or compound substance, made up of at least two elements, like water, hydrogen, and oxygen. If we got a mixture, we can further subdivide the mixture into homogeneous, that is uniform throughout, solutions, dissolved down at the molecular level, or heterogeneous, where it's not dissolved, that things are mixed, but they have chunks bigger than molecular. A good example of heterogeneous mixture is reinforced concrete. You've got the Portland cement, the aggregate, the little rocks, and the rebar, the steel rods. All mixed together, but not dissolved. Dalton's atomic theory starts with an ancient idea that matter is made up of atoms. And he said if this is the case, then we can redefine what we mean by an element. That is, an element is a type of atom. Furthermore, we can define what we mean by a compound substance. Compound substance made up of at least two different types of atoms. And furthermore, since Dalton thought of the atom as the ultimate building block, he said in a chemical reaction, the atoms you start with are the atoms you end up with. Atoms are not created or destroyed. The only thing that changes in a chemical reaction are the bonds between atoms. It's marriage and divorce. You get married, you got the same people you started with, they're just now bonded. You get divorced, you end up with the same people you started with, they're no longer bonded. Mendeleev and Meyer independently came up with the same bright idea, and that is, if you organize the elements in terms of elements that have common properties and put them in a column, you find that properties repeat periodically with increasing mass. Furthermore, wherever there's a gap in your periodic table, you assume that there must be an element that exists to fill that gap. And using the trends that are now obvious in the table, you can predict the properties of that undiscovered element. The modern periodic table. The 2016 International Union of Pure and Applied Chemistry's recommended compact format for the periodic table. We can divide the elements into three basic categories: metals, metalloids, and nonmetals. Note that there's a lot more metals than anything else in the periodic table. Although we divide the elements into metals, metalloids, and nonmetals, there's really not a sharp dividing line. There's a trend. As you head towards the lower left towards francium, things become more metallic. As you go towards the upper right towards fluorine, things become less metallic. In the periodic table, the groups are vertical columns of elements that share some chemistry, and so they're sometimes referred to as a family of elements. The periods are horizontal rows, and there are 7 of them. The alkali metals are lithium, sodium, potassium, rubidium, cesium, and francium. Note that all hydrogen is in that column. It's really not an alkali metal. We have to put it somewhere, and it does share a little chemistry with the alkali metals, but it also shares some chemistry with the halogens we'll talk about in a minute. Beryllium, magnesium, calcium, strontium, barium, and radium make up the alkali earth metal family. The alkali earth metals are slightly less reactive than the alkali metals. The halogens, fluorine, chlorine, bromine, iodine, acetylene, are all non-metals. Fluorine is the most reactive non-metal of all. The noble or inert gases, helium, neon, argon, krypton, xenon, radon, are chemically unreactive. In fact, they're so chemically unreactive that the family wasn't discovered until after Mendeleev and Meyer had developed their first table. The transition metals are a block of elements in the center of the table that share some chemistry. There's more than one column there, and so I call them chemical cousins rather than a family. The lanthanides are a row of elements that chemically resemble each other. Like the lanthanides, the actinides are a row of elements that chemically resemble each other. All the actinides are radioactive, and most of them are synthetic. 19th century electromagnetic theory predicted that the Rutherford model of the atom should not be stable. The electron should spiral into the nucleus, destroying the atom within a fraction of a second. Niels Bohr proposed a way to stabilize the electrons. He said, perhaps the electron's energies are quantized. If the electron energies are quantized, then not just any old orbit will work. Only certain orbits are allowed. And this keeps the electrons from spiraling and crashing into the nucleus. In the Bohr model of the atom, the electrons are arranged in specific orbits. Because of this, each element has a very specific arrangement of the electrons. We call the electronic configuration. It's the electronic configuration that determines all of your chemical properties of the atom. Now, the most important electrons are obviously the ones on the outside, called the outermost shell, or the valence electrons. Elements in the same family have the same number of valence electrons, and this is why their chemistry is so similar. A chemical formula tells you which elements and how many atoms of each. Noble gases are less reactive than the other elements because when you look at them you realize that their valence shells are filled, or the first two subshells of their valence shell are filled. So what you can do is, to figure out the chemical bonding of other elements, is say, what do we have to do in terms of electrons to get to a noble gas configuration? Chemical bonding is all about shifting electrons around to get to a more stable electronic configuration, that is, noble gas-like. In ionic bonding, we're shifting electrons from one atom to another. In covalent bonding, we're pooling some electrons and sharing them between two atoms. If sodium gives up its one electron in shell 3, shell 2 now becomes the highest occupied shell. And it's got 8 electrons, which is a noble gas number of electrons. Sodium now has the same number of electrons as neon. Chlorine, it's got 7 electrons in its valence shell. If it takes the 1 electron from sodium, it now has 8 electrons in its valence shell, and chlorine now has exactly the same number of electrons as argon. Both the sodium and the chlorine end up with a noble gas configuration. In sodium chloride, the positive charge of the sodium is exactly balanced by the negative charge of the chloride anion. In magnesium chloride, on the other hand, the magnesium cation is a double positive charge, so you need 2 chloride anions to balance it. Because the charges have to balance in the ionic compound, if you know the charge of the cation, the charge of the anion, you can then predict the formula, and vice versa. There is an easy trick for getting the formula if you know the charges of the ions. Take the charge of the cation, and that becomes the subscript of the anion. Take the charge of the anion, and that becomes the subscript of the cation. If you look at iron, you got Fe3+ and oxygen O2-, and then look at the iron oxide. It's Fe2O3. The charge of the oxygen has become the subscript of the iron, and the charge of the iron has become the subscript of the oxygen. It's a bit like the trick you used for adding fractions back in elementary school, where they had you do the cross multiplying and you got the least common denominator. Same sort of thing. A pair of electrons being shared is a covalent bond. So for sharing 2 electrons, it's a single bond. For sharing 2 pairs of electrons, it's a double bond. 3 pairs of electrons, a triple bond. Each hydrogen atom starts with 1 electron in orbit around it. When they covalently bond, they're now sharing those electrons, so each hydrogen atom has 2 electrons orbiting around it, which is the same number of electrons that helium has orbiting around it, and of course helium's a noble gas. If the shared electrons are shared equally, then we call this nonpolar covalent bonding. Whenever 2 different elements bond, the shared electrons will be unequally shared because each different element has a different degree of attraction for those electrons. Nomenclature is how you go about naming chemical compounds. We start off looking at the simplest ones, binary compounds. In a binary compound, you've got 2 elements. You can have more than 2 atoms, but only 2 types of atoms for it to be binary. You can recognize a binary compound by the IDE ending. The second element has the last few letters of its name removed and replaced by the suffix IDE. So chlorine becomes chloride, sulfur becomes sulfide. For ionic compounds, the cation, which is usually a metal, comes first, and then the anion comes second. The anion is usually a nonmetal. Occasionally you run into compounds, particularly with transition metals, where the metal can have more than one charge. Copper, for example, can be +1 or +2, which means there's two different copper chlorides. So that we know which copper chloride is you're talking about, we put a Roman numeral parentheses following the copper that tells you that it's either the +1 or the +2. Copper 1 chloride is a copper with the +1 charge. Copper 2 chloride is a copper with the +2 charge. Covalent compounds are usually made up of nonmetals. The one that's closer to fluorine on the periodic table typically goes second. We also have to specify the actual numbers of atoms in the compound. So we use the prefixes mono, di, tri, tetra, penta, and hexa. And so you have carbon monoxide and carbon dioxide. You might want to check out the Coalition to Ban Dihydrogen Monoxide website. Polyatomic anions are a cluster of atoms covalently bonded together that have a charge. Your polyatomic oxyanions can be recognized by the ATE ending. So we have nitrate, sulfate, phosphate, and carbonate polyatomic oxoanions. Atoms are not created or destroyed in chemical reactions, only bonds. So when we say the equation must be balanced, we mean that the atoms you start with are the atoms you end up with. Only the bonding changes, not the atoms themselves. If you look at the first reaction, we're taking hydrogen and oxygen to form water. On the left-hand side, we've got two hydrogen molecules. Each molecule's got two hydrogen atoms in it. The subscripts tell you how many atoms. The big number out in front tells you how many molecules. We've got one oxygen molecule made up of two oxygen atoms. So on the left-hand side, we've got a total of 4 hydrogen atoms and 2 oxygen atoms. If you look at the right-hand side, we've got 2 water molecules, which means we've got a total of 4 hydrogen atoms and 2 oxygen atoms. The number of oxygen and hydrogen atoms on the right is balanced by the number of hydrogen and oxygen atoms on the left.